The Dance of Vectors and Matrices, a Mathematical Tango. In the elegant ballroom of linear algebra, vectors and matrices engage in a captivating dance, their interactions producing unexpected and fascinating results. Let's explore this mathematical tango. So in problem 8.9, using the square matrices in problem 8.8, so the last question, and the column matrices alpha and beta, we are tasked with finding a variety of products: A alpha, alpha dagger beta, alpha transpose B beta, and then alpha beta dagger. Pretty interesting, and we'll see why all of these run their course. We've seen A and B time and time again throughout the quantum mechanics class, and this one looks like a projection operator, so it definitely plays a role too. In part A, we have the multiplication of a square matrix with a column vector. In this case, we have to be very careful to make sure the dimensions match, as kind of preluded to last video. So A from last time was given here, which is a 3 by 3. It constitutes 3 rows and 3 columns, whereas alpha is a 3 by 1, which constitutes 3 rows and 1 column. As we remember, we need to take this row and multiply it into this column via a dot product, and this creates this entry here. And then we have this row to this column gives us the middle entry. Following that, we have last row to the column brings us to this entry. Now, remember last time when I mentioned inner dimensions must match? Well, the inner dimensions here are 3 and 3. And we also said last time that the outer dimensions 3 and 1 would be the result. And that's what we see here. So also recall that the first matrix, in this case A, guides the rows as seen in the outer dimension. So 3, 3, 3, the purple 3 here, 3 rows here gives us a 3 rows. While the second matrix, or the B from last video, guided the columns. So we have one column here, and we end up with one column here. So it all comes together in this nice little intertwining of vector and matrix manipulation and mechanics. Once we go ahead and now multiply this out, we can simplify it. And then we see that this leads to I plus 2I plus 2I, or negative I, 2I plus 0 plus 6, minus 2 plus 4 plus 4. All that comes together to our 3 by 1 finale. Now, if we want, we could think about this as the waltz of matrix and vector. Imagine a matrix as a skilled dance instructor guiding a vector through a series of intricate steps. When the matrix A leads vector alpha, they create a mesmerizing performance. This result is like a graceful twirl, transforming the original vector into a new form. And as such, we see that in quantum mechanics, this is an operator. This vector is a state vector, so when an operator acts on the state vector, we get a new vector or a new state. And that's why we like to use matrices and matrix mechanics to explain ourselves in the language of math for quantum mechanics. Moving on to part B, this time we have the multiplication of two vectors. In this case, we're tasked with alpha dagger beta, which, remember, the dagger was the Hermitian conjugate, which told us to take the transpose and then take the conjugate of the transpose, and then multiply by beta. Of course, all of these multiplications are the form of a quote dot product instead of a cross product, but we'll get the cross product in the last part where we see the quote outer product. So that being said, our alpha was a 3 by 1. Taking the transpose makes it a 1 by 3. Taking the conjugate turns the signs on the complex parts of this. That being said, our inner dimensions here match 3 and 3, and our outer dimensions tell us what result we're going to have. So taking this row, multiplying it into this column, leaves us with this here, which again is a scalar, so we get a 1 by 1. Now, if we want, we could think about this as the intimate duet. When two vectors come together, they perform a close embrace, resulting in a scalar value. This scalar product is akin to the chemistry between dance partners, distilling their interactions into a single complex number. Moving on to part C, the multiplication of two vectors in a square matrix. Okay, so this is going to be a lot to take in, and again, the PDF for the patrons has all the little details here, but be mindful that all we really showed in the vector space axioms was that we were associative. Nothing to do with commutativity, because most matrices don't commute. That being said, because we did show associativity, it doesn't matter if we multiply the alpha transpose with the B matrix or the B matrix with the beta matrix. Either way it goes, we're good to go. In this case, it'd be easiest to tackle it, in my opinion, from left to right, just because that's the natural order. As such, we have to look at, if we take the transpose here, we get a 1 by 3. The B matrix from 8.8 was 3 by 3 as well. So the inner dimensions match, and our outer dimensions are what are going to be the resulting product. And then we see here, row to column, row to column, row to column. That will give us a 1 by 3. Which looks kind of hard to type, but it runs its course. First element here from row to column, second element here, row to second column, and then our final element from this row to the last column is right here. Of course, we can simplify this, and we see that here. Now that we know we have a 1 by 3, this leads us to multiplying into the beta vector here, which is a 3 by 1. Again, inner dimensions match, so our outer dimensions are the result, which is what we see here. This row to this column leads to our dot product here. And we see, once again, that we end up with a scalar, because it's 1 by 1. We just have to simplify. Distribute all this together. We see that happens in this bracket. Multiply the zeros. We love zeros, clearly. And then once we simplify this down, we end up with a scalar number, which is 8 plus 4i. Now, if you'd like to think about this, this can be considered a grand ensemble. In a more elaborate routine, we see a vector leading a matrix, which then guides another vector. This trio creates a scalar finale. It's as if one dancer whispers instructions to the matrix, which then directs the final movement of the second dancer. So all these things come together in a great way of dancing with vectors and matrices. It's actually really cool to see this come out. Lastly, we have the multiplication of two vectors in a different way than we saw in part B. This time, we have alpha and beta dagger, but again, remember that the dagger means conjugate transpose. So alpha being a 3 by 1, taking the transpose and conjugate of beta turns it into a 1 by 3. So this tells you that we have a 2, 1 plus I instead of minus I, and a 0. Now again, the inner dimensions here match, so our outer dimensions are the result. Whereas when we had A dagger beta or alpha dagger beta, we ended up with the 1 by 1. This time we have a 3 by 3. So this is often called the outer product as compared to the inner product where we're looking at the overlap. As a result, taking this row, which is just I, to each element of each column, I, then we have 2i, 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 and then 2, 2, 2. We see that once again, the leading matrix or vector gives us the rows, and then the 2, 1 plus I, 0, 2, 1 plus I, 0 give us the columns. Pretty darn cool. As a result, this is a 3 by 3, but it's pretty simple to compute. So once we distribute these or simplify all the elements, we see we get our resulting matrix, which is a 3 by 3. So our check is complete. Now, this, if you would like, we can consider the mirror dance. Finally, we witness the outer product where the vectors create a matrix through their interaction. This is like two dancers moving in perfect synchronization, their combined movements painting a complex pattern in the form of a matrix. Pretty darn cool. In this mathematical choreography, vectors and matrices intertwine, creating a performance that is both precise and beautiful. Each interaction reveals the hidden harmonies of linear algebra, transforming abstract concepts into a dance of numbers and dimensions. Very, very cool. That was a lot of fun, and I was not expecting to create a mathematical poem or, dance translation, so to speak, for this. But when I saw that and read it, and I had to, modify it for this, of course, but that was pretty darn cool, and it's definitely an insightful way to tell you about the interactions of vectors and matrices, and be very, very mindful of not only the way to multiply them, but also the resulting dimensions as the multiplication happens. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I also just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting this channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.